Welcome back. In this video, we're going to finish up chapter 13 by looking at a couple other properties of liquids, specifically viscosity and surface tension, and recap how these properties are related to the intermolecular forces of those molecules. Surface tension. This is related to the energy that's needed to increase the surface area of a liquid. Well, what does that mean? What do we mean when we talk about the energy needed to increase the surface area? Well, so let's say that you have a droplet of water. And within a droplet of water, you have water molecules that are interacting with each other. And the surface tension is going to be a function of how those molecules interact with each other, the strength at which they interact. At the surface of the water, what we see is that there are fewer numbers of interactions. On any given water molecule, what we see is that it's being pulled in not in fully opposite directions. There's nothing pulling upwards at the surface. What this does is this makes the surface tense. And therefore, it makes them higher in energy because they have fewer interactions. So the surface area is minimized in order to reduce the energy. Therefore, in order to increase the surface area, it's going to require energy. The surface tension of a liquid is what allows, for the case of water, something like a water strider to walk on the water. Because of the surface tension, it's strong enough for it to support the weight of certain objects. Viscosity is similar to surface tension in the sense of we're going to find that it's related to the intermolecular forces. This viscosity is a measure of a liquid's resistance to flow. So if you take olive oil, for example, and pour it out of a bottle, it is much less viscous than honey. Honey pours very slowly. And the reason for this is because honey has higher and more intermolecular forces versus the olive oil. What has been observed as well is that there's a temperature dependence upon viscosity. If you were to heat up a liquid, its viscosity is going to decrease. So if you take honey at 25 degrees Celsius and olive oil at 25 degrees Celsius, the honey will pour more slowly. However, you can increase the honey's temperature to a point that they flow at the same rate. So let's summarize what we've learned about liquids in terms of their macroscopic properties. All the liquid properties that we've discussed are based on intermolecular forces. If a substance has high intermolecular forces, that's going to decrease the vapor pressure because the molecules are going to be more attracted to each other in the liquid, and it will be harder for them to escape into the gas phase. Because of this, it's going to take a higher temperature in order to convert all of our liquid into a gas, and therefore the boiling point will be higher. High IMFs lead to high surface tension because the molecules are attracting each other and making it harder to increase the surface area of the liquid. And then high intermolecular forces also lead to high viscosity because viscosity is the resistance to flow. If there's high intermolecular forces, the molecules are attracted to each other and they don't very easily move around. Let's do a practice problem here to finish out this video. Assume that the substances shown are liquid at room temperature. Which one would you expect to have the greatest viscosity? Pause the video and try to determine this on your own. Welcome back. So what do we know about viscosity? We know that for a substance, comparing substances, we can look at their intermolecular forces. Higher intermolecular forces will lead to higher viscosity. So let's evaluate these two substances for the various types of intermolecular forces. We want to first look for hydrogen bonding. We want to look at polarity, and then potentially molar mass and shape, depending on the first characteristics. We can rule out any type of ion interactions because neither of these have ions involved. So for molecule A, it is neither a hydrogen bond donor nor an acceptor. However, for molecule B, it has two different sites that are able to both accept hydrogen bonds and donate hydrogen bonds. Therefore, molecule B has hydrogen bonding, while A does not. If we were to look at the polarities, the carbon-sulfur bond is not nearly as polar as the carbon-nitrogen or the carbon-oxygen bonds. And so molecule B overall would be more polar than molecule A. If you look at the molar masses, there's not going to be a significant difference in the London dispersion forces based on the molar mass because they are approximately the same. And the shape isn't going to come into a factor as much as well. They're both relatively the same shape, and there's a much larger difference in polarity and due to the hydrogen bonding. Therefore, molecule B is going to have the greatest viscosity. That's it for this video. Thanks for watching, and have a great day.